Okay, welcome everyone to Physics 203 Class 8. This class is on the Compton effect, which is a fascinating piece of physics which was discovered a little bit later than the photoelectric effect and the black body radiation in the 1920s, but as we'll see, combines not only quantum physics in explaining it, but also special relativity. And we'll delve just a teensy bit into special relativity in this lecture. We'll cover it in a lot more depth later in this class. So the Compton effect, we have to start thinking about scattering light from matter. So if we send light into a piece of metal or a rock or something, what does classical physics predict? So here's, again, our classical picture of light with oscillating electric and magnetic fields. And here's a loosely held electron within a matter. So you can imagine this as part of a much larger solid. So what is going to happen to that electron? Well, the electric field is going to exert forces on it and gradually make it uh, force it up and down and vibrate it up and down. And vibrating and accelerating charges, vibrating charges are accelerating charges, and the frequency of vibration of this electron will be the same as the frequency at which this electromagnetic wave passes. So what we can say is that the electron re-radiates, in fact, in all directions, not just in the same direction, at the same frequency as the incident light or radiation, and therefore at the same wavelength. So classically, that's the theory of it is, the math of it is rather involved, but that's conceptually what we see, that electrons radiate at the same frequency at which they are um, irradiated. So Arthur Holly Compton, an American physicist at, I believe, Washington University in St. Louis in the early 1920s, was doing some experiments in so-called solid state physics and found an interesting result. He sent X-rays, of course, a form of radiation, with they have a fairly short wavelength. They're very energetic, with this particular wavelength of 0.071 nanometers off of a carbon target. And he saw both X-rays at this same incident wavelength of 0.071 nanometers, so the same wavelength as uh, as the electrons in the carbon were being bombarded with. However, as well as X-rays at a somewhat longer wavelength. So here's the data taken from our textbook. This is his taken from his paper actually, and reproduced in our textbook. This is his X-ray spectrum here, and this down here is his detected spectrum. Okay, so what we see is that the incident X-rays are highly concentrated around a certain wavelength, which here is measured as using diffraction as a glancing angle from a calcite crystal, but is proportional to wavelength. So we could convert this to wavelength if we had the right proportionality constant. So the incident is highly concentrated around one direction, and then some of the output radiation is at that same wavelength, but some of it is shifted over toward higher wavelengths. So this is the part which is scattered, happens to be scattered and measured at 135 degrees from the incoming direction. So that would be if the incoming direction were to the right, then at 0 degrees, 135 degrees would be back and to the left. And this second peak, which Compton detected, simply can't be explained classically. There's just no way that an electron in the carbon, when radiated with X-rays at this wavelength or frequency, can radiate at a just slightly larger wavelength and slightly smaller frequency. So something was going on here, and Compton tried to figure out what was going on. So he took the new physics proposed by Einstein and others of viewing X-rays and radiation as photon particles, as bundles of light rather than waves. And here's a diagram of the collision. So here is the incoming X-ray. Here is where we have E is equal to HF. The energy of the photon is equal to Planck's constant times frequency, which should hopefully be familiar from blackbody radiation and the photoelectric effect. And then we have the target electron, which can be hit here. And you'll see this formula, E of that electron is mc squared. So E equals mc squared. That's the first appearance in our modern physics class. Effectively, the photon is traveling so fast, even though the electron may be moving at a couple thousand meters per second, it's effectively at rest. So we can take the electron to just have this is called the rest energy, E equals mc squared. And then after the interaction, we have the photon scattered at a given angle, theta, and the electron also recoils by conservation of momentum. We have to have some downward momentum afterwards at an angle phi. So let's fill in a little gap here. We're actually using both quantum physics, which treats this X-ray as a photon, and special relativity, as you can see with this E equals mc squared. So a big result from relativity, which we'll study later, and actually which rather than E equals mc squared, I believe should actually be on all the mugs and t-shirts, is this one. Okay, it's not as pretty as E equals mc squared, but it's actually a little bit more powerful. It says that E squared is equal to mc squared squared plus p squared c squared. Okay, it's a little bit more of a mouthful, I admit. But if we look at two limiting cases of that, if m equals 0, as it is for the radiation for the photon, it has 0 mass. If m equals 0, this term disappears. M equals 0, this term is gone, and we have E squared equals p squared c squared. Taking the square root, we get E is equal to p times c, and from that we can get that the momentum p of the radiation is equal to its energy, E, over the speed of light, so p is equal to E over c. And then we've already established or become familiar with E is equal to HF, so this would be HF over c, and then since c is equal to f times lambda, this becomes f over f, lambda in the denominator. So the momentum of the X-ray photon is h over its wavelength, where h is, again, Planck's constant. On the other hand, we could take p is equal to 0, the momentum is equal to 0. That makes something as at rest, it has no momentum in a given reference frame. And in that case, this part disappears, this p squared plus c squared. And so then we have E squared is equal to mc squared squared. Taking the square root of both sides, we get E is equal to mc squared. So you can see why this formula is useful. It combines treatment of the rest mass of massive objects and the relativity of the photon and radiation all in one nice formula. Okay, so there's my little advertisement. So what does that leave us? Um, Again, here's our diagram. Now we understand that momentum of the incident X-ray photon is h over lambda. We just found that. The target electron, since it's at rest, has E equals mc squared. The recoil electron has final energy equal to EE, where this is the relativistic mass energy, which again we'll study more later. And the scattered photon has energy hf prime, where f prime, the frequency can be different from the incident photon in principle. And so P is equal to h over lambda prime, where lambda prime is the potentially shifted wavelength of the scattered photon. So we set up conservation equations. Those are big in physics. Conservation of energy would be, our initial energy would be the photon, hf, plus the electron, mc squared. And our final energy would be a scattered photon, hf prime, plus the energy of the recoil electron. Momentum-wise, in the x direction, taking x horizontally here, as usual, we have beforehand just the incident photon, h over lambda, since the electron is taken to be still. And afterwards, we have to use some trigonometry. We take the x component of both the momentum of the photon, which would be h over lambda prime cosine theta, that would be this part, the x part, plus PE. PE isn't shown on the diagram, but that would be the momentum of the electron, the recoil electron, times cosine of phi. And then finally, for the y direction, we just take the vertical components. There's no vertical momentum in the photon or the electron, initial electron, before the collision. So the vertical components, h over lambda sine theta, which would be the vertical side, must be equal to the momentum of the electron times sine theta. Okay, so we have these three equations actually in 1, 2, 3, 4 unknowns, 3 equations and 4 unknowns. And so it's not uniquely determined, and that's because the angle theta can range freely. So we get radiation at all different thetas. So it doesn't pin down a particular theta. Okay, so we do lots of algebra. It's in the textbook, a half or 2/3 of a page of algebra. We eliminate the variable, for now the variable phi, involving the recoil electron, because we're interested in the scattered X-rays. And this leads to the following formula. The change in wavelength between the incident photon and the scattered photon is equal to this quantity h over mc times 1 minus cosine theta. Okay, so after all that relativity and quantum physics, we get a fairly simple formula. So here again is a part of Compton's data, and his incident wavelength was 0.071 nanometers in X-ray, and then since these angles here on this axis are proportional to wavelength, I extrapolated and did a proportionality relationship and found that this peak, the second peak, is at 0.075 nanometers. So therefore, experimentally and according to Compton, the change would be 0.004 nanometers, 0.075 minus 0.071. Theoretically, according to our analysis here in conservation equations, we should have h over mc, where m is the mass of the target electron, times 1 minus cosine theta, where theta is the angle that the detector was looking, which in this case was 135. So we plug in an h over the mass, this is the mass of the electron in kilograms, times c, times 1 minus cosine of 135. And that looks like it's just a repeat of the previous slide. And we find that if we solve this, we find delta lambda theoretical is equal to, again, 0.004 nanometers. So by looking at these, the incident photon and the electron as particles, and using conservation of energy, momentum, and in the x and y directions, that's the quantum part, and then the special relativity to relate the momentum and the energy, we find that we can account for this unusual shift in wavelength. So some follow-up and significance. Here for the fifth straight slide is our diagram of the interaction. Notice though that most of the outgoing radiation at 135 degrees is shifted, but some of it is unmodified. So how can we explain that in modern physics? In classical physics, that's what's expected. The wavelength in is equal to the wavelength out. But in quantum mechanics, it seems like our analysis is telling us the wavelength should be shifted. And so what about the modern theory of this unmodified peak? Well, in that case, what's thought is that rather than scattering the X-ray hitting a loosely bound electron, which can interact on its own, it's hitting a tightly bound, an inner core electron. For those of you chemists in the S or P shells, in the inner core electrons, and that transfers, that means the effective mass that it's dealing with is essentially the nucleus and the whole atom, because you can't move those inner electrons without moving the nucleus and the atom. So we can take the same formula, Compton's scattering formula. Delta lambda is lambda minus lambda prime h over mc1 minus cosine theta. But since the mass, now we have a different mass, right? Because the effective mass, if we're hitting a tightly bound electron, is not the mass of a single electron, but the mass of the atom. And that's a factor of about 1,000 times greater, roughly speaking. And so therefore, we divide by something 1,000 times larger, and our wavelength change, delta lambda, is 1,000 times smaller, too small to be detected at the time. Although I believe it has been detected now. So in fact, the modern theory is that this peak, this peak here, which Compton thought was unmodified, is actually just shifted ever so slightly by 1/1000th of 0.004 nanometers. So very interesting. So just to follow up, data on the recoil of the electron's angle. We talked most about the photon. Others studied the recoil electron's angle and energy were taken in the next couple years, and the expected results were found, expected energies and the expected distribution with respect to angle. This confirmed Compton's theory and led to his Nobel Prize in 1927, so good for him. And although, as I said earlier, this came later than black body radiation or the photoelectric effect, so it wasn't right at the forefront of the change from classical to quantum physics, it is a fascinating effect in that it combines two modern theories, quantum physics and special relativity, in explaining this this curious result here, this shift in wavelength. All right. I hope you've enjoyed this discussion and learned from it, and I will see you in class soon. Thank you.